All right. Hi again, everyone. Here to torture you some more. Um, so how long do we have? 40 minutes. 40 minutes. Cool. Sweet. Okay, so we're going to talk about all the generic data loaders in YT. And let me please.
Hard to add a new theme that you could just switch with. Going to JSON to do it.
Yeah, okay. So generic data loaders in YT. So generic data loaders help you get your data into YT when your data does not have a dedicated front end. So if you try a YT.load and you get an error in your data, you can look to these generic data loaders. So if with some copy. And they actually are like kind of developed to the point where oftentimes they're all you need. Like you don't necessarily need a full dedicated front end, which really helps you get your data into YT faster and also cuts down on development time and all of the stuff that goes with that. So and generally they support both gridded data and particle data. Caveats that we'll get into. Some links to the docs here. Oh, I did modify a bunch of stuff, so you'll want to pull from the repository. That'll also get you all the volume rendering stuff I just pushed too. So you'll be set for a while. But in any case, so if you want to click on those docs, that's where you can do that. So that's an overview of what the different loading functions are. So we have a bunch of loaders all focused on structured grids. So there's load uniform grid, load AMR grids, load octree, load HDF5 file. We have a loader for particles, load particles. And then we have some loaders for unstructured grids. So these are essentially finite element meshes, so we have the load unstructured mesh and load hexahedral mesh. I'm not actually going to demonstrate these today, but if you have unstructured mesh data, I have done a fair bit with loading unsupported unstructured meshes in IT. And there's one notebook later that does it for some output from a geodynamic code aspect that is PPK PVTU files. So it walks through in gory detail how to do that. But generally the approach to try to not do everything manually because loading in like the connectivity and coordinates for finite element meshes can get really complicated. So it's helpful to use their intermediate tools to load those in and then load those into YT. Okay, so let's get on more to other stuff. So we saw load particles a bit yesterday with Matt. And so I wanted to just touch on a little bit more on that, particular how to use it to load in SPH data, which I don't think we've done yet. But so you have to first answer these questions. So first, can you fit all of your particles in memory? If you can, that's good. You can use load particles. You only have one SPH particle type. If that's the case, this will work. If you have more, it will not work, but you could potentially load them as separate data sets. But if you want to plot them all at once, that gets pretty tricky. And then you need a density mass and smoothing link fields defined. So if you have all of those things, then we can use load particles to load SPH data. So this cell down here shows you how to do that. Let me just scroll down. So I was trying to just make it not be totally random data. Hence this cell's a little bit longer than it could be. But down at the bottom, we have load particles, where we're supplying a dictionary of data, something about the length unit, and the bounding box. So all this data dictionary, find up here, is fairly simple. So you need to define the particle positions X, Y, Z for your field, and then you need density, mass, and then smoothing link fields. And so these are all normally distributed fields for all of these, and then the particle position is a function I made up, but just something that'll give something that's not random. Otherwise, the plots are not obvious, obviously doing anything. Let's load that in, and let's just pull up a slice plot. And here we go, get a slice through our SPH data. That's neat. And everything else should work for you as well. So this is an off-axis projection plot data as well. So that's pretty easy. So if you have, was there a question? No. So if you have SPH data that's sitting in some file format that YT can't support, and you can fit most of it in data or subsets of it data, you can use this directly and you'll get pretty much full support for everything in YT that SPH particles work for. Okay, cool. So that's all I was going to say about SPH particles. Any questions on that?
Actually, I have a question. So when there's some indexing happening when you use SPH particles. So I guess when you're loading from disk, this index is not stored. It's cached for when you have a big SPH data set.
Yeah.
There's some like
Stream it doesn't do any.
So the rest of this time is gonna be about sorry, I was jumping around on me here. So we're gonna talk about load uniform grid and load AMR grid and then load HDF file. So load uniform grid, if you can answer yes to all of these, you should use load uniform grid. So do you have a single grid with cell-centered values and it's easy to load? Can you fit at least one field in memory? And is your grid regular? So this can mean either uniform. So a uniform grid in YT speak is delta X, delta Y, delta Z. They can differ from each other, but they're fixed in each dimension, or a stretched grid. So these are grids where delta X, delta Y, and delta Z are one-dimensional functions of their own dimension. So they can vary along, delta X can vary along X, but it's fixed across Y. So let's go ahead and do this. So load uniform grid, very similar to load particles, where you supply lots of arguments here. So you supply a data dictionary with NumPy arrays and units, or possibly functions, which we'll get into later. You supply the dimensions of your arrays, and then lots of optional arguments for length unit and bounding box. Also very useful, you can specify the geometry and ordering of your axes, which I won't go into now, but if you have spherical data, you can load uniform grid as well. And yeah, so very similar to before, we have our load uniform grid, we're supplying a data dictionary, a shape, and this case is a stretched grid. So you supply the cell widths. So what this looks like, actually computing it. So it starts off by calculating some widths of cells in each dimension, X, Y, and Z dimensions. So these are all normal distributions to give some variation. And then just for convenience and to make my bounding boxes go from 0 to 1, this normalizes the cell width so that when you add them up, you get 1 in each dimension. That's a data dictionary, uniform grid, and when you do a slice plot through this and use this annotate cell edges callback, what you get are all your cells with, you can see that they're varying along each dimension. So this is our stretched grid in action here. One of the things that load uniform grid and can do for you is split is you can supply this nprox argument, which will subdivide your data into a number of grids. So you do that and call annotate grids. You'll see some grid lines showing up. So YT will go and process each of these grids independently as it's making these plots or as you're doing all your data subselections. But since we did initially load this in memory into our array to do this, you still have to be able to fit that memory or that array in memory. Which brings us to some of the cool newer stuff in YT in terms of the loaders. So if you read through this whole docstring for load uniform grids, the data argument description is pretty long. So there's this bit here. Functions may also be supplied in place of NumPy arrays, as long as blah, 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 blah. So this is cool and pretty powerful. So what does this actually mean? So instead of our data dictionary being an array, you can have a function. So you can, that's actually wrong, let me fix that. So it's a function handle that's not evaluated when you pass it in. So you replace your NumPy array with a function handle that you write to do something, sorry. Stop double clicking. So this function handle can do anything you want, as long as it conforms to some rules in terms of its arguments and outputs, which means you can do a whole bunch of cool stuff. And so I've built a lot of stuff on top of this functionality. So YTxArray is a package that I wrote and maintain that essentially just uses all these generic data loaders in ways to inject handles to like open data sets from elsewhere. So in about 7 lines, this is the summary of what YTxArray does. So it imports Xarray, which lets you load like netcdf files, regular gridded arrays, pretty common in the geosciences to use it. It opens up that data set, which does not read any data, it just reads metadata. And then I write a function that accepts the expected parameters for load uniform grid, which we're going to talk about. And within that function, I write a whole bunch of other stuff that does a lot of processing of that grid object and field handle, and forgot to put this, sorry, one more change in here. So in this function, I put a reference to that open dataset handle. And because it's globally defined within the function, it's reading from the outside scope. It's already open, it's in this function, and you can pass this function handle to the data dictionary, and then when YT goes to read in the grid data, it will call this function from within this function, which just lets you kind of do a bunch of stuff with YT that would normally you would have to like write a full front end for. And we'll go into this a little bit more detail. But in terms of what the grid object and field tuple arguments are, so these generic functions. So a grid object is a data container kind of that represents an individual grid within YT. So if we have our data set that we already have our data set that we subdivided into some grids. So if you access the index attribute, and it'll be an underlying grids attribute, which is just a list of all the grids in the data set. And so if you just pull one out, you get a single grid, and this has a whole bunch of attributes hanging off of it. And what I mostly to do this sort of like embedded wrapping process is just pull out the left edge, the right edge, and then the shape of that grid. And then up in this function, I'll just take those bounds in that shape and do like an interpolation from one data set to this grid and load that into YT. And then that second argument field tuple is just a normal YT field. So this is a field type, and then the field name. This I forgot to update. We're not actually going to go through it. That's just describing that a little bit more. Okay, so this is for load uniform grid we've been talking about, but still load uniform grid is still a single grid, even though it can split things up. you get a little bit more flexibility when you start using load AMR grids. So let's talk about that a little bit. So load AMR grids is like load uniform grid, but it's a lot more flexible. So instead of a data dictionary, you give it a list of grid dictionaries, and an individual grid dictionary describes a given grid. So it's a left edge, a right edge, the dimensions of your grid, the level that that grid is at, and then all the fields defined for that grid. And just like load uniform grid, these entries can either be NumPy arrays with or without units attached, or they can also be functions. And so, example does that. So let me run this first, and then I'll walk you through a little bit about what this is doing. Okay, so what this function or this cell block here is doing is it's setting up a little mini AMR grid with some levels of refinement. So setting these up by hand like this is a little bit finicky because you have to make sure cell edges align exactly between levels. Otherwise, you get errors when you load things into P. So if you read through this in detail, which I'm not going to do too much of right now, what it does is it sets up a domain and then divides the domain width by 2 and then puts a new grid right centered on the whole domain, and then just does that iteratively, making sure that all the cell edges align. And so at each level, it's defining one of these grid dictionaries and adding it to our list of all the grids. And then down at the bottom, it just gives that list of the grids, the size of the base level and the bounding box, and then length units. And so now, let's just plot this up. This is a slice plot through this one field that I defined, which is so it's the grid level plus some noise essentially. And so what you see is our finer and finer grids. Also, I will mention that these are using a couple plot callbacks that we didn't talk about explicitly. So one is set log false, so it's just turning off the log on the color bar, and then the second one is setting a CMAP using from the EMYT color maps. I like this pastel one. It's kind of pretty. And so if we annotate the cell edges for this, you can see the refinement a little bit more clearly. So coarser cells to finer and finer cells, and if we zoom in just to the middle, up in this plot, the cell edges are kind of really masking out the underlying data. You can see the detail of those inner cells. So if you have AMR data that is not supported by YT, you can use this load AMR function to get it into YT. You just have to in air quotes, parse your AMR structure and coerce it into this grid dictionary format, which I recognize could be kind of hard, but it probably is a little simpler than writing a full front end, initially at least. But let's go back to our function. So remember how in load uniform grid, instead of data, you can give it a function. So our grid dictionaries here, these NumPy arrays could instead be functions, and they could potentially load from files. And so what this gives you is true lazy evaluation by grid within YT. So you can load data that does not fit into memory now without having to write a full front end. And that is how this load HDF file works. So it's essentially load AMR grids that uses this function callable functionality to load from an HDF file. So this cell here does that. So it creates a HDF5 file to work with. So this file is called hello.h5, opens it up, creates this root node, creates an array of 512 by 512 by 512, writes it into our HDF file, just so that you have an HDF file to read. And then load HDF5 file, you give it the name of the file, the root node to read from. So, this is cool data. So we put cool data, and it will read all of the fields, I think, at that, or it will add those fields, all of the fields that are available at that root node. and some other stuff. So let's run that first. And just look at some of the output. So we don't give it a bounding box, so it will assume 0 to 1, which is fine for us. And it's this line here, auto guessing 512 chunks from a size of that big number. So that big number is 512 cubed. So that's how many elements are in an array. And it'll default to making grids that are 64 by 64 by 64. So you end up with 512 chunks in this data set. And that means that when you, for example, subselect a region and then give it to a slice plot or any other operation, you can get out, a plot of your data with all the grids. YT will only be loading from file these grids as it needs them because we're using this function within our data dictionary that read from that HDF file on demand just by chunk. Yeah, so that is pretty powerful unless you do lots of kind of crazy stuff. Like I've spent a lot of time working with ZAR files, which split up uniform arrays into lots of little tiny chunks. And so I can use this to just load those ZAR files into YT in a lazy way. So you can work with larger than memory data, lots of it and stuff that otherwise would take a lot of work to get into YT.
With telling it is defining a function, is that what?
The width of up here.
You go up. Let's go back to.
Oh,
that width. What is that?
Yeah, width is not the most common instruction in Python. Oh, I shouldn't mansplain for you.
No, which width? Sorry, which width?
With H5
width.
file.
Oh, this width. Sorry.
Context.
So this is a construct in H5 that opens up a file, and then outside of this with context, it just closes it for you. So you could instead replace this with DS. Wait, I reused a file or a variable name here that I shouldn't have. But you could do H5 pi.file, my file, open it for writing, do your stuff, and then you have to explicitly close that.
The width manages that.
Yeah, so the context manager will call it.
You're writing to an HTML.
Yeah.
H5 file.
Yeah. Yeah, so this create data set will write to that file because it's open for writing and then it gets closed.
Do the same actually with just the open to open a file, and then you with open the name of the file, and whenever you're doing the with statement, that it actually closes the file on your behalf. It's quite nice to prevent having unclosed file references.
Sometimes they have error handling and things like that as well.
And it's especially useful for HDF5 because sometimes if you're opening an HDF5 for writing, you can't open a second time. It's locking the file, and so if you do it in a script in Python and then you're not closing the script, you can't open it again in another Python, or you've actually closed it in the first. The with statement, it's only open for the time of the statement.
Cool. So that's kind of all I had for this.
That's great.
Any questions or?
I'm not sure if you commented on this early when you were talking about particle data, but one of your questions there to like assess whether to open with particle data says you only have one SPH particle type. Is there a way of dealing with SPH data which has, multiple species particles?
Yes. So if you specify them as tuples for the field names, it should be able to distinguish between different particle types.
And would you be passing like an ASCII file to this?
You could.
But you would have to write the code to load from the ASCII file.
Oh, right, because you're passing, I see, yeah, because you need this array, to pass to it.
Yeah.
Okay.
With an H5 file, I think that load particles also take callables now.
No, it should, but
Okay.
it doesn't. Matt, you were saying though that, so you were saying that if you give it a different field name, so that does not work right now. And I don't, I think. Yeah, it'll give you an error right away saying that you can only have one SPH type.
Oh, one SPH type. Yeah. Okay.
Which I don't think is like, I think that should be fixable. pretty
Yeah,
easily,
it should be.
because we haven't.
Let's take a
implemented
look
it,
at that.
yeah.
The C question. Is free large supply identical by enzyme? How they?
Wait, sorry, could you face this way?
I'm sorry, this three lines, the right hand side look identical to me, then why, how the left hand side?
So how are the, the three functions, get
Oh.
X, Y, or Z, how are they returning different things? Is that the right question?
Oh, because,
yes.
yeah, it's using a random sampling. It's like a random perturbation, which adds a little.
Oh, okay.
So it's just
So
random.
It's just random, yeah.
Okay,
Yeah,
okay,
yeah,
thank you.
sorry. But even if they were the same, it wouldn't really matter for this point. You would just end up with like clusters of particles more closer than what you get without that randomization.
Great. All right, thank you, Chris. Excellent. Okay, lunch should be out there, I would imagine. Although we are 10 minutes